What we know about earthquakes is empirical. So that means we have a few large earthquakes that have been well recorded, and they have been used to come up with empirical relationships that, for example, tell us how much shaking we expect in which distance to an earthquake source. But the reality is much more complicated. And to use the simulation results that we're producing helps to better really understand the complexity of earthquake shaking. It helps us also to better assess, for example, what's the worst case scenario, what's the maximum magnitude an earthquake can have. Then we've been really interested in recent large earthquakes, such as in Turkey or in California, that jumped from fault to fault. So we've been modeling these events and trying to understand what drives earthquakes connecting faults and jumping from segment to segment. What are the driving factors of that? My name is Alice Gabriel. I'm a guest professor of earthquake physics at LMU Munich in Germany, and I'm also an Associate Professor of Geophysics at the Scripps Institution of Oceanography in UC San Diego. And I'm one of the PIs of the GEOS project. SeisSol stands for Seismic Solver. It was originally developed to be the most accurate code to model seismic waves, so shaking and waves that travel through the Earth using supercomputers. And over the last decade or so, we've been optimizing it to be still the most accurate, or so very accurate, but not as expensive. And we also extended it a lot to include earthquake physics. So we're not only interested in the shaking and the ground motions, but we're really interested in what happens at the source of this shaking. So what happens during earthquakes when they start, how they rupture geological structures, and how they stop. What we also did is we extended the code to model not only earthquakes and seismic waves, but also sound waves that travel through the atmosphere, and gravity waves that are tsunami that travel through the ocean. So we're really interested in the multiphysics effects of earthquakes in tsunami generation and in all kinds of waves that they're producing. SeisSol has been part of the first part of GEOS already, and it's now also part of the second phase. And in the second phase, we are linking SeisSol to other communities. We're really interested in linking to the tsunami community, also to the long-term geodynamics community. So these are scientists that are interested in the long-term evolution, plate tectonics, or how Earth or other planets shape. And they can give us important information to better understand earthquakes that are not on the same timescales that we are. What we specifically did is that we were for the first time able to use all of the observations we have, so the data that we're recording during earthquakes, and feed them into the code and produce simulation results that we can directly compare. And that is just not possible if you do simple models in 2D, or if you don't have these kind of capacities.